our final chemistry senior seminar of the season. Jesse's going to be telling us about his research today, and Deanna Donahue is going to be introducing him.
Welcome, everybody. I'm so glad you could join us today as we get to hear about more stuff about air. And I have been so happy to work with Jesse on this project. I think that Jesse comes to us from Maine and has done so many things at Lawrence and has so many interests that as he came into my office and we started talking about projects, I kept thinking that this is a really great project. From talking about how do you define something that's undefinable because we don't know enough, to very practical questions, and kind of having a project that spanned that whole breadth of ideas. I think it was a really fun time for me and Jesse together. And so it's been good fun, and I'm excited for him to present it. His diverse sets of interests is going to take him not to chemistry, not to voice, but onto a career in kind of game programming in the future. So I hope that in this talk you can see the many different skills that Jesse brings, and it has been a pleasure to work with you on it.
All right, can you hear me? All right, so welcome to my presentation. And today I'm going to be talking about indoor air quality in one of our on-campus buildings, in particular, Brokaw Hall. So basically how this talk is going to go, first I'm going to talk about some background information to help build some context for the project, and then the specifics of the project that I was looking at, and also finally looking at the results, what we found and what we did not find. So I'm going to be talking about air a lot in this presentation, and I'm just like to get some common idea of what I mean by air and what is a part of air. So the majority of air, it's made up by three major components. About 2/3 of air is nitrogen gas. It's inert, it's all around us. And then most of the remaining portion is oxygen. That's what we need to live. And then argon is the third major component, coming in at just under 1% of air. And then everything else we talk about in air falls under these other category. Less than 1%, about 0.04% of air are these other components of air. This is mostly CO2. It also includes other trace gases, like a few other noble gases. And then this is where we also find air pollution. Another component of air is water vapor. The issue with water vapor is that it varies wildly depending on where you are and what the climate is like and what the weather is like. So that's why it's not included in this pie chart, because it could be anywhere from less than 1% to more than 5%, depending on where you are. So I'm going to be mostly focusing on indoor air in this talk. Basically, I'm going to start by talking about why indoor air is different from outdoor air. You've probably heard a lot about outdoor air and how air works in the environment. Generally speaking, in an outdoor environment, there's some kind of wind or a breeze, or there's just a large volume of air such that any kind of pollutant will get dispersed and distributed throughout a larger area, a larger volume. Whereas with an indoor space, typically a lot of the air is just kind of circulating around, and pollutants tend to stay inside the building unless there's good ventilation. And ventilation is what brings the air from indoors to outdoors or from outdoors to indoors. And yeah, ventilation is super important if we're talking about the quality of indoor air. And if we are going to talk about broad generalities, and if we want to characterize indoor air versus outdoor air generally, outdoor air tends towards dispersion, where pollutants are spread out and diluted, whereas indoor air tend to be characterized by concentration, where pollutants stay and accumulate unless they are vented out. So indoor air quality is a really major concern. People spend as much as 90% of their time indoors, especially in an industrialized society. And it varies from person to person, but for people at like college students or college workers, it could be even more than 90%. It could be an extremely large portion of their life spent indoors. Air quality problems can have really significant health effects on people. It can lead to lower quality of life. It can lead to illnesses. And approximately 3.8 million people die every year because of indoor air pollution, according to the WHO. So this is that's a lot of people every year, and that includes various different sources of indoor air pollution, like carbon monoxide poisoning and secondhand smoke. But it is a really major concern, especially since indoor air is generally worse than outdoor air, because in outdoor air, you have all the pollutants that you find outdoors, which is a concern for sure. But then in indoor air, you have all of those same pollutants as well as extra pollutants that are generated indoors. So it can really be a problem for it to have good indoor air. Generally, when people are thinking about measuring indoor air quality and what are the things that people try to measure, there's generally two categories. There's things that we want to keep as low as possible, things we want to minimize, and things where we want to find a sweet spot where it's the perfect amount for the comfort and health of the inhabitants. Things that we want to minimize include pollutants like volatile organic compounds, or VOCs, particulate matter, gases such as carbon dioxide, carbon monoxide, nitrogen dioxide, sulfur dioxide, or ozone, and also radon that is found in a lot of homes. And then there's also pathogens like viruses that can be floating around in the air, and we want to keep those down as well. And then there's things like humidity, temperature, the motion of the air, like whether it's moving around, being blown around by fans, or whether it's still, that we want to find a sweet spot for so that people are comfortable. And then there's light and noise, which aren't directly air necessarily, but it's the environment of the indoor space that we want so that people can be comfortable. So generally, when we're talking about indoor air, it's useful to categorize it in terms of, is it good, is it bad, so that we can kind of identify which air is problematic and which air is just great. So generally, a lot of data is compiled into an indoor air quality score, like an air quality index. And so it's generally divided into levels of like bad to good, essentially. And that way you can quickly look at this combined score and say whether there's a problem or not. And then if there is a problem, that's when you can look into the data and see where the problem is coming from. But if the air quality is good, you can quickly identify good air by calculating this air quality score. And there are many different ways of doing it. These are two examples of systems that have air quality scores. The one on the left is directly pertaining to this project. So something that I've found and I've been reading about when I was reading about indoor air quality is this thing called sick building syndrome. And sick building syndrome is kind of an umbrella term for a lot of different symptoms that people experience. Generally, it refers to you enter a building and you start to feel sick in some way. You feel kind of yucky. And the symptoms can vary. Some people might not experience any symptoms. And generally, when you leave the building, the symptoms improve. And the cause is it's not easy to identify. It's generally, if we're calling it sick building syndrome, it's because we haven't really found one cause yet. Once we found a cause for it, generally we would call it something else, more specific to what's causing it. So sick building syndrome, it's very elusive because the symptoms are varied and no one knows why people might be feeling ill. Different people might be more likely or less likely to feel ill, depending on their biology and other health conditions that they might have. And so some of the symptoms that you might have with sick building syndrome are things like headaches, neurological things like tiredness or dizziness or irritability, irritation in the eyes or in the nose and throat, or even skin irritation, or asthma-like symptoms like having trouble breathing or coughing or things like that. So we've been receiving reports. We've been receiving feedback from people who are in the second floor of Brokaw Hall. These are the office spaces on the second floor, that some people have been going into the office and starting to feel yucky, starting to feel bad symptoms coming up that would typically go away once they had left the building. And the cause, the symptoms would vary. It wouldn't be just one thing, and the cause was unclear. So that piqued our interest, and we started to wonder, could this be a problem with the air in Brokaw Hall? Could there be some issue with the air quality? Could it even be sick building syndrome? So that's the question I'm going to try to answer with this project. We already had some air sensors available to us. We had some sensors that we had acquired at the start of the COVID-19 pandemic. We were trying to assess whether the indoor air on campuses was likely to be spreading COVID-19. So we have two different sensors that we have. We have the aware element sensor, which is primarily designed for in-home use, and then the aware omni sensor, which is designed for commercial use in a business. And both of these sensors measure temperature, humidity, carbon dioxide, volatile organic compounds, and particulate matter. The omni sensor also measures light and noise. And so some of the features that these sensors have is one of the coolest things about these sensors is that they basically calibrate themselves. They're super easy to calibrate because they're designed for use by the general public. It's a very simple process to calibrate them. The data that they collect is uploaded onto an online dashboard that you can access through the internet, and that allows for monitoring the data basically in real time, and you can see the history of the data, and you can also download it and put it in a spreadsheet and analyze it in other ways. It does require continuous electricity and an internet connection for this to work. One of the nice things about these sensors is that they're all in one sensor, so you don't have different sensors for each thing you're trying to measure. And the price is somewhere in the hundreds of dollars for these kinds of sensors, which is a lot cheaper compared to some of the other options, which could be in the thousands or tens of thousands of dollars per sensor. So considering what these sensors can measure and how many of them we were able to get, it's a very cost-effective option, which is really great for us. So this is kind of a floor plan of the second floor offices in Brokaw Hall where we were setting up these sensors. Essentially, we deployed 4 sensors. We put one in the hallway near the stairwell where people would be passing by. There was one sensor in the desk, on a desk in the main space of the office. And then we put 2 sensors in 2 of the cubicles in the office where people had set up their workspaces. So because of the sensors we were using and because of how we had set them up, we were able to see our results pretty much almost immediately. And these sensors have been collecting data continuously since December. We set them up in December of 2021. So we have several months of data we can look at now, and we can sort of interpret the results and see if we can come to some conclusions about them. So the first thing we thought might be giving people issues is volatile organic compounds. This was something that we thought, if there's a lot of these in the air, that could be a potential culprit. So volatile means that it evaporates rapidly at room temperature, and organic means that it's a carbon-based molecule. It's based on carbon and hydrogen bonds. So that's a very broad definition. There are many different types of volatile organic compounds, and similarly, their health effects vary wildly. Some are not very harmful at all. Some are very harmful. So it's really a mixed bag. Some VOCs also have a strong smell. I've got 3 examples here of 3 different VOCs that you might be familiar with. There's formaldehyde, which is a very common VOC, toluene, and isopropyl alcohol. So you can see that they vary in size and complexity, and all 3 of these examples are things that our sensors can measure, and all 3 of these are ones that you generally don't want to be breathing for a prolonged period of time. That can give you some bad effects to your health. So this is the data that we've collected from December through April. I have to count on my fingers every time I change a number month into a name month. It's just, but basically what we found is that the VOC data is pretty good. I've grouped them into categories based on like green and yellow and orange and red. Red is higher than this chart goes, but basically what we see is that the vast majority of the time we are in the lowest green category of excellent quality. That is not something, this graph is not something that was concerning to us, because while it does spike up into the yellow and into the orange categories, when we're looking at VOCs, that's not something that we think would actually cause problems. If it stayed up there in those higher categories, we'd be concerned. But with VOCs, we're generally looking for prolonged exposure in order to cause negative effects. And if we look at, for example, the average, I took the average, the minimum, the maximum for all of these different sensors. And the averages are well within the excellent category of quality. Anywhere less than 300 parts per billion is considered excellent for VOCs. So the next thing that we wanted to look at was particulate matter. And basically, there's 2 different, particulate matter is generally categorized into 2 different categories. There's PM10, which refers to particles less than 10 micrometers in diameter. These tend to fall out of the air after a short time. They tend not to linger in the air for a long period of time. And they're also unlikely to enter into the lungs when you breathe them in. They're more likely to get stuck in your nose or in your mouth. Whereas PM2.5, on the other hand, these are smaller particles with diameter less than 2.5 micrometers. They tend to be more numerous when they're present, and they stay in the air longer because they're lighter. They can kind of float around without falling to the ground as much. And they are small enough to get into your lungs. They could get stuck in your mouth or your nose, but they could also penetrate into your lungs. And the PM2.5, that's what our sensors were designed to be able to measure. Our sensors don't measure the PM10. So if we look at the PM2.5 data that we have, it looks pretty good, except that there's one day, which was February 1st, where it did not look so good. And so on the sensors, there's a little display that shows you the air quality score. And the people who were in the office were noticing that the score was dropping down very low on February 1st. So they called Deanna up and they were like, hey, we're seeing a really bad score on our sensors. Should this be something we should be scared about? So Deanna went over to take a look, and it turns out there was some construction going on, and they had set up a big dumpster right next to the air intake for the ventilation system of the building. So as they were putting a bunch of stuff into the dumpster, a lot of particles were being generated, and that was going straight into the air intake and into the room where people were working. So that was just for one day. But generally, other than that, we see excellent quality of air just based on particulate matter. Nothing on this graph is really concerning to us. It pretty much is always within the green, and it's pretty much always within the excellent quality of the dark green color. So the next thing that we were looking at is also CO2. CO2 is the fourth most abundant gas in the atmosphere. It's poisonous to humans at high concentrations, but at low levels, it's harmless. Our body is designed to function with some amount of CO2 because CO2 is a product of the human body. The largest sinks for CO2 are plants and soil and the ocean, and none of those exist, at least to any large extent, within an indoor space. So in an indoor area, there's really very little to take CO2 out of the air. It kind of just stays in the air until it gets ventilated out. And so we can look at CO2 to be able to tell something about our ventilation rate, how much the air is being vented out. And so just looking a little bit more on how that works, we have this idea of the steady state of CO2, where we have a source of CO2, which in this case is exhalation, people breathing. That's contributing to CO2, and then ventilation is taking CO2 out of the air and into outdoor air, and then bringing in outdoor air to replace it. So when people enter a room, eventually it'll reach a point where there's a steady state, where the rate at which CO2 is being generated in the air is equal to the rate at which it's being taken out of the air by ventilation. And so we can basically know about our ventilation rate based on how much CO2 is in the air with people inhabiting the room. So if we wanted to think about how this ideally would look, we would start at a CO2 level that is the baseline CO2 level, which is around 400 parts per million, maybe 410, 420. It keeps increasing every year. And then people enter the room, and that number goes up. As people are exhaling, they're producing CO2 and releasing it into the air. Eventually, we reach a steady state where it's being produced at the same rate as it's being taken out by the ventilation. And then when people leave, it drops back down as the air is being exchanged with outdoor air, and it reaches the level that it is in outdoor air, which is the baseline CO2 level. So if we're going to look at the data that we've gotten, this is, again, all of the data from December until April. Generally, if we're thinking about CO2 in terms of as a health hazard for humans, the numbers we're seeing look pretty great. Anything less than 1,000 parts per million is considered perfectly safe for humans to breathe. And the numbers we're having, it's for the most part less than 600 parts per million, which that's the category that's considered excellent. No concern here in terms of CO2 actually causing people to feel sick. If we want to look at CO2 from the perspective of the steady state of CO2 to talk about ventilation, this is 1 week of data from our sensors, 1 week in late February. And we can see that when people are in the room during the daytime, we do reach approximately a steady state of CO2, where the ventilation rate is equal to the rate of production of CO2. Approximately, right? It's an approximation. And then when people leave the room, it goes back down to the baseline CO2, which is around 415, 420 parts per million, which is what we would expect because that's the outdoor level of CO2. And based on the rate at which the CO2 declines once people leave the room and how long it takes for it to reach the outdoor level of CO2, there's some easy calculation you can do that basically gives you how many times the air gets exchanged with outdoor air per hour. And we can tell that the air in this room is being exchanged with outdoor air approximately 0.5 to 2 times per hour. So that's a pretty good ventilation rate. It means that probably we don't have pollutants accumulating very much. It is less than it is in some other buildings, but it is a pretty good ventilation rate. Another thing that our sensors can measure is light and noise. This is a little bit tangential to my project, so I'm not going to talk about it at great length. But basically, it can affect people's ability to concentrate. It can affect people's comfort and even give people headaches. And one of the issues with our light data is that it seems like the sensors were not detecting light very well. One of the sensors was detecting an extremely low level of light, which was unrealistic. I kind of ignored the light data, but I did look at the noise levels, and they're about what you would expect for an indoor office. They seemed like perfectly fine, comfortable noise levels. Then the last thing I wanted to talk about was temperature and humidity. These are kind of grouped together because humidity also affects the perception of temperature, and they both affect how comfortable you feel in the room, and they can even affect your health in the room as well. If there's a high temperature and a high humidity, that can cause you to sweat, which will cause odors to be produced, and it'll cause you to feel uncomfortable, and so we don't want that outcome. Also, dry air can lead to dehydration. It can lead to breathing issues. If you already have a breathing problem, dry air can make it worse. And also, the humidity can affect the shape and size of particulate matter because water molecules in the air can condense onto the surface of particles, making them bigger and more likely to fall out of the air. So there is a link between the two, which I won't really talk about anymore, but I'll just leave you with that information. Looking at temperature, 2 of the sensors that we had deployed, we had placed them right next to a window and also right above a radiator. So both of those contributed to really big variations in the temperature that they were measuring. So we basically decided that those measurements from those sensors were not reliable, so we ignored them. But we did look at the sensor in the main space of the office and the sensor in the hallway, and we found that they were measuring pretty reasonable amounts of temperature, about 21 to 25 degrees Celsius or 70 to 77 degrees Fahrenheit. And it varies depending on person, what temperature you like it to be at, but generally this is considered a pretty good indoor temperature, not something that struck us as particularly concerning. And then humidity is the other thing. Humidity was much too dry. And you can kind of see that it was often dipping down into the red region where it's the most concerning, less than 15% humidity. The ideal level of humidity would be somewhere around 40 to 50%, and it was very rarely going that high. It was mostly staying within the orange and yellow, so really not great. And here's the thing. This isn't just a problem with this building. This is a problem with all of the buildings on campus during the winter. And really, any any climate that experiences winter all across the globe has this issue, where the buildings are too dry in the winter, and this gives people problems. And so it's not specific to this building, it's not even specific to Lawrence, but it is a concern, and it is something that we saw in our data that we thought could use some improvement. So bringing all of this together to answer the question that I sought out to answer, is second floor of Brokaw Hall a sick building? It's really hard to say based on the data we've collected. I think that it would require some further study. Based on the data we collected, the air quality is pretty good. There was nothing that seemed concerning at all, except for maybe the humidity, which is a problem everywhere. And so nothing seemed to be amiss. However, that doesn't mean that there couldn't be something else going on that could be leading to people to feel ill. Maybe it's some other aspect of the air that we didn't measure, or perhaps it's not even in the air at all. Perhaps it's something else that we're not considering yet. So what's something we can do next to help measure the air of Brokaw Hall? Ozone is a gas that is harmful to humans if you breathe them in, and that's a common indoor air pollutant. So one thing we could try next is to measure ozone. There are other gases like nitrogen dioxide and sulfur dioxide that could give people bad health. Also, the larger size of particulate matter, the PM10, that's something we could measure. But some of the problems is that there's a lack of low-cost sensors. We are very fortunate that these sensors that we had are as cheap as they are, considering what they can measure. Because, like, for example, an ozone sensor might cost in the tens of thousands of dollars. And that ozone sensor is probably also going to be very loud. And so it's disruptive to set it up where people are working because it produces a lot of noise. And so noise can also lead to other health effects like problems concentrating and headaches. So that was something that would interfere with our further abilities to investigate. So having not identified any cause for people to feel sick, what can we do nonetheless to try to improve the outcomes, even if we don't know what's causing it? I am not a health expert, I'm a chemist, so I really can't prescribe anything without there being some further investigation, and that, I think, if we are going to implement a solution, that's what we would need. We would need to look into it further. But based on my readings and based on the data I saw, some things that we could try that might improve the situation are potentially setting up a humidifier during the cold months, during the winter, to bring that humidity level up, ideally to at least 40% humidity. Also, the ventilation rate. There have been studies that show that when you increase the ventilation rate, prevalence of sick building syndrome goes down, and that's been one of the few things that can reliably reduce sick building syndrome, is increasing ventilation. So that is something we could try. And also another thing is fans. If the air is moving too slow or moving too fast, we could try turning fans on or turning them off and seeing if that helps. But again, I'm not quite sure. I don't know exactly what would solve the issue. And I would like to thank Professor Deanna Donahue, who is my senior experience advisor. I don't think I could have possibly done this without her. She was extremely valuable to me for completing this project. Professor Rachel Dowdy, the professor for the senior seminar, for guiding us through the process of making the slides and organizing peer feedback. Eder Bellegarde and Joe Heyman were two students that I worked very closely over the several weeks to work on giving feedback for the project and working on making the slides. I'd also like to thank Aaron Chu, Professor Donahue and also Isaiah Grace, who helped me practice presenting the slides and also gave me feedback on them, and Lawrence University, who gave me this opportunity to pursue this project and gave me the resources that the project required. These are my sources. Most of my outside information I got from this top source, but then also all of these other sources helped me gain a more full understanding of the issue, and I essentially used them all to build my understanding. And that's it.
All right. Jesse is ready to take your questions about his presentation. Evelyn.
Like the construction that you mentioned, were there other variables you had to consider when throughout your collection and interpretation of the data,
Other variables I haven't considered?
or that you had to consider throughout your collection of the data?
I'm not sure I understand.
Like the construction that you mentioned, that's why we saw like a huge peak on the graph. Were there other things that like also contributed to your data?
So it's really hard to say because I don't know what's going on in these buildings. I would say that you can kind of, especially if you look at like the CO2 data, you can kind of do some speculation. You can say, like, you could probably say that on this Wednesday night, someone was probably in the office late, and that's why we see such a high amount of carbon dioxide late into the night. But that's just speculation. I don't really know. And so for the most part, I would say that I don't really know what all the variables are that go into these values and what other factors there could be. There could be many factors contributing to all of these measurements.
Samantha?
Have there been any complaints of other buildings on campus where people are exhibiting sick building syndrome or symptoms that seem like it, that maybe a project like this could be expanded to?
Yes, we have sensors like these all across campus. Some are in the con. I think we have a couple sensors in Andrew Commons as well, and also in the library. And yeah, we have been looking into the library as a place where a lot of people go, and some people have been...
On that second floor stacked section, people have reported feeling ill.
Yeah, so we are looking into the library as well as a place that needs investigation.
Okay.
But so far, we haven't seen anything that's that concerning. I mean, if we have, we would first tell facility services. So far, nothing that makes us too scared.
Justin.
Yeah, I was just wondering, what are the most common side effects that people are like reporting in the second floor?
That's a good question, and I don't know.
I don't know either.
Yeah.
I don't feel like that's information we felt comfortable asking. We just got told that we were getting reports of feeling ill.
Yeah, and a lot of the time with issues of indoor air quality, a lot of the time that's all you have to work with is just there might be some kind of problem.
Chris.
So do you think the use of isopropyl alcohol because of COVID actually make your data higher than it should be?
Ooh, that's an interesting question. No, I don't think so. Deanna is giving me a shake of the head. But I see what you're getting at with isopropyl alcohol being used to disinfect, I think. But Deanna's shaking her head, so I'm going to trust her.
You see it more consistently and in a very different pattern and with many more like very consistent spikes all across campus, and that's we haven't seen that anywhere.
I have a question about the particulate matter. So you can sort of detect levels of the different sizes of matter. Is there any way to detect what type of matter it is, or what source it might be coming from? Like, for example, you knew the construction was happening. Is there a way to identify particulate matter coming from an office product or a certain visitor?
Not with the sensors we had. Maybe if you have a very expensive piece of equipment, like a mass spectrometer, but not with what we had.
Could you collect, like if the sensor reported a high value on that day, could you go in and collect an air sample and then take it back to the lab for analysis?
Yeah, I suppose we could.
Have to rely on the office people being observant for that. Mike?
I'm curious about your VOC graph that you had.
Mm-hmm.
There were a couple of real spikes in there. Okay.
Yeah, like these ones here.
Yeah. Was anything kind of reported on those days? Yes, those two really just kind of like stuck out to me.
Yeah, those are the ones that
Did
go
they
into the
report
orange.
anything on those specific days that something may have been going on?
No, I don't think there was anything reported. Let's see, where's there was construction on February 2nd, so where was that would have been,
That's a little bit farther down.
yeah, so this is not quite there.
Right.
So
it looks like the first one is like 1.3, okay. When we get back into school, the other one is around 123, 124, somewhere around there. And it's just like, I'm curious.
So this is beyond Jesse's project because it is looking also at the library data. Sometimes we get spikes that are in multiple buildings at the same time for VOCs. And that tells me that it's coming from a plume outside. And I think those big spikes, I'd have to go back and double check because I didn't double check right before I came. But the library and Brokaw were having some VOC spikes that spiked at the same time. That's one data point, right? So it's hard to know if that's even real. The only reason I think it could be real is because you saw it in multiple locations. But that's probably an outdoor air spike.
Samantha?
I know this is kind of leading off into that tangent. This just made me think of something is when you say the plume that happens, like there's just kind of that interesting like sewery smell that kind of goes around campus periodically. And I wonder if maybe that has something to do with it possibly. Maybe that would be something else to measure at some point.
the witch that goes around campus?
There's like a sewer-like smell that sometimes just goes around all of campus on some days that I'm like, if it's getting consistent readings across different buildings, I wonder if that's sort of...
Yeah, I know what you're talking about, and I smell it too. I haven't seen anything. I would have to look into the data more and actually probably record which days that I can smell that smell. So it would take some more investigation, but I don't think that you... it's hard to say. I don't think that it would show up, but it really depends on what is causing the smell. It could be one of these things that we're not measuring, or if it is caused by a volatile organic compound, maybe we could see it, but it's hard to say.
Justin?
Yeah, I guess this kind of relates back to what Rachel was asking, but is the sensor collecting like all the air that it filters through? Is it like going, or that it is detecting, is it going through a filter that you could potentially analyze that filter at some point, or no?
Deanna's shaking her head, so I'm going to say no.
Okay.
You would have to pump to do that, and pumps are loud.
Okay.
Yeah.
All right. We've all got all of our questions for Jesse asked. Let's go ahead and thank him again one more time. Thank you for joining us.